Okay, thanks. Yeah. So, yeah, hi everyone. Welcome to the IARCS verification seminar series, and we are happy to have Supratik here with us today. Supratik, as you know, is a professor in the computer science department at IIT Bombay, and he has worked on, of course, a variety of problems in the areas of formal verification, automated synthesis, model counting, logic, finite model theory, SMT solving, many others. Yeah. So So without taking much time, I'll just let Supratik do the talking. Yeah. So Supratik, over to you.
Yeah. Thanks, Madhukar. Thanks, Deepak. Thanks for the invitation. Good evening, afternoon, morning, wherever you are. So I'm going to talk today about some work that we did jointly with Hazen Torfa, who's currently at Chalmers University in Sweden, and Shetal Shah and Isakshay from IIT Bombay, and Sanjit Seshia from Berkeley. And this talk will be about synthesizing Pareto-Optimal interpretations for black box ML models. And I'm going to tell you what this Pareto-Optimality is about, and also, why, basically, how do we deal with this thing about black box ML models, and why do we even want to talk about black box ML models? Okay, so some introductory slides. I guess all of us are quite familiar with this, that machine learning applications are in all over the place. And it's kind of becoming important that we be able to provide some kind of explanation about what these machine learning components are doing in these various applications. Because the kind of components that we are using are like deep neural networks, which are complex and they're hard to comprehend. And when they take certain decisions, it's very hard to look at the structure of the deep neural network and say, okay, this is kind of the reasoning that it followed to take this decision. But at the same time, providing some kind of explanation, even if it is not the exact sequence of firing of neurons, but at least explaining at a certain abstract level the behavior of these machine learning components is becoming a necessity. And there are emerging regulations like GDPR, which require that, if there is a consequence, then you have to be able to explain for legal purposes how the decision was taken. So there's a need for tools, techniques, algorithms to synthesize targeted interpretations with formal guarantees on their correctness. Now, what do I mean by targeted interpretations? The same machine learning model, maybe the same DNN, may be used in different kinds of environmental contexts, and it may produce different kinds of results. So whenever we want to come up with an explanation, we want to say that, okay, in this environment, under this context, it behaves this way, and under certain other context, it behaves that way. That's one part of the targeted interpretation part. And the other is, I can always say, okay, here is a deep neural network, and here is an explanation for it, which is an equally large decision tree, maybe. And that maybe doesn't suffice for several purposes, because the decision tree itself may be too complex. So we want to give some control to the user to say, okay, how complicated, how big these interpretations can the user handle for the ML models. But whatever we generate, we want to give some formal guarantees on their correctness. So we will see examples of this, as the talk proceeds. So the larger sort of goal that we are working towards is to come up with models that are explainable. However, this explainability business is kind of very tricky. I mean, what is explainable to me may not be explainable to you. So we will see some kinds of approximations of this. By no means am I saying that this is the way to explain what a machine learning model is doing, but at least we will see some approximations to it, and we will see that the framework that I'm going to talk about will actually allow you to do other kinds of explanations as well. Okay, so the literature actually has a lot of work on this. So, for example, there are synthesis of optimal decision trees, decision rules, linear models, and there are. I mean, let me not read out the titles of the papers, but essentially there is work on it, and this is quite an active area. So, what all of these approaches basically do is that, any such interpretation that we're trying to come up with, any such explanation that we're trying to come up with, first of all, must be able to replicate the decisions that the machine learning model is doing, right? I mean, for example, if for a particular input, the machine learning model says yes, and for another input, the machine learning model says no, then whatever explanation or interpretation I'm trying to come up with, maybe a decision tree or a set of decision rules, that should also say yes and no for those two respective inputs. Uh, but then, as I was saying, if this decision tree itself becomes too large, or if the number of decision rules itself becomes too large, maybe it's not so much quote unquote explainable. So typically the literature, what is done is that these two things, the requirement for accuracy, that I should be able to predict what the machine learning model was doing using my explanation or interpretation, and this thing about the structure, that it should not be too large, or it should not be too many rules or something. So all of these, typically what they're done in the literature is that they're folded into a single objective function. So you give some weightage to this, to the accuracy, some weightage to the maybe the structure, whatever cost you want to put on the structure. And then once you come up with the single objective function with some heuristically chosen weighting of the two, the two parts, accuracy and the structural part, which helps in, uh, telling us whether something is explainable or not. Then you optimize the single objective formulation, and then you say, okay, once I found an optimal value, once I found an interpretation that optimizes this combined single objective function, that is kind of my best explanation. Now, it turns out that this is not always, I'll actually show you examples, but this is not always the best way to do it, because when you're combining which something like accuracy and something like maybe the height or width of a tree or the number of nodes in the tree, when you're trying to combine these two numbers with some weight function, depending on how you weigh them, you may or may not be able to see some of the possible interpretations or explanations. So really, interpretation synthesis is an optimization problem with at least two different conflicting objectives. One is the correctness or accuracy, and the other metrics approximating explainability. And why do I say they're conflicting? Because if I want to get a very highly accurate model, then probably it will become as large as the original, let's say, deep neural network. And so it will not be very understandable or explainable. Whereas if I want to get a very, highly explainable thing, maybe it's very small and simple and everybody understands it immediately on seeing it, then it is unlikely that's going to be really, be replicating the predictions of the complex machine learning model, because the reason we have such complex machine learning models is because perhaps there are no simple ways to arrive at these decisions, right? I mean, if there's a simple way to classify images, why would we go into deep neural networks for these images? So these two are kind of, in tension with each other. If you want something which is highly accurate, then maybe it starts becoming complex. And if you want something which is simple, maybe it starts losing accuracy. And this is kind of not just about, when I'm trying to build explainable things, it's about a lot of other things. A complex model may actually uh, take more time to execute if we want that to be an executable model. Or it may actually have more cost in terms of, how it can be used in some other applications. So really there are these two conflicting things. If you want something to be very accurate, you're probably coming closer and closer to the actual complex machine learning artifact. But that's exactly what we want to move away from. We want to come up with something which is easier to understand than the complex machine learning object, component. So, and there is this work in the literature on structural risk minimization, which says that this is to be expected. As the model complexity becomes large, you can increase the confidence. And of course, as the model complexity increases, the risk, which is the amount of misprediction you're doing, comes down. But then these large models are probably also more difficult to understand and explain, right? So is everybody fine with me over here? Is everybody with me? This is kind of just trying to set up the context that why do we want to do this. And the reason, I talked about these black box ML models, because if I don't consider them as black box, I'm really looking at probably very large models if I want to look under the hood, thousands, maybe millions of nodes and all of that. So the question is, can we abstract away from that and still build something which is meaningful and which has some formal guarantees? And we'll of course see, what kind of guarantees these are. But the reason we emphasize on black box models is that we don't really want to be bothered about how complex that original model was. Whatever method we come up with should be able to address it for arbitrary complexity. Okay. Srivas, I can't hear you. Are you trying to say something?
No. I didn't ask any question, but
Okay.
I had a question, Marian, because see, I don't, are you going to be formally defining what explainability and explainable models are?
Yeah.
Because,
So
uh, right now, maybe there is, this area is new to me. And therefore, is there a formal definition of explainable model coming up?
no, I mean, you've hit the nail on its head, because as I said, what is explainable to you may not be explainable to me. So what we'll show is, a kind of framework where different metrics of explainability can be incorporated. And the experiments that I'll show are with a specific metric of explainability, and I'll explain what that is. But that is by no means the final word on what explainability means. It's, there's a lot of there's a lot of variance in what you call an explainable model.
Yeah, so I presume by explainable model meaning you are going to synthesize some alternative given a machine learning model, say like a DNN. You're going to synthesize some object, okay,
Yes,
the decision tree that in some sense behaves the same way as the original one,
almost the same way. Yeah,
uh, and and yet it gives some insight into why
exactly,
such a decision.
exactly. So I guess once I show you some examples which are there in the next
So,
slide, you'll
so
see
Supratik,
what I mean. Yeah,
yeah. So one more question I had, just with very specific, maybe clarification question.
yeah,
So in this right side, you have this model complexity, and I was just trying to understand the empirical risk and the confidence you're talking about. Is it about the predictions that the models are making, or what?
yeah. So the confidence is in the accuracy of the prediction, and the risk is, the higher the confidence, the lower the risk,
Okay, yeah. Thanks.
right? Okay, so given that there is this tension between how accurate we want to make the model, and how complex we are making, how easily understandable it will be, what we'll try to do is we'll present a method which basically explores some Pareto-optimal interpretations, which try to balance these two in some way. And very interestingly, what we find is that there is not a unique or single Pareto-optimal interpretation. There is actually a host of them, and each one of them is incomparable to the other. So it's not that one of them dominates the other. So we'll see this towards the end of the talk, what comes out. Okay, so the rest of the talk is structured like this. And so I'll first start off with an example. I'll give the formal problem definition, and then I'll show how it can be reduced to quantitative constraint solving. We are using MaxSat. This is not necessarily the only way to do it, but this is how we do it. And then we'll talk about how to explore the Pareto-optimal space, what kind of guarantees we can give, and some results. Okay, so let's talk about an example. I hope you can see this little the video at the, is the video visible? I mean, can somebody confirm? It actually shows an aeroplane with the propeller turning. I don't know whether the turning of
Yeah, we can see that.
right, and it's kind of taxiing on a runway. And the problem that we're trying to solve is, this is actually a neural network that comes from Boeing, which uses camera images to estimate cross-track error, that is the distance to the center line of the runway, to keep the aircraft as it is taxiing on the runway sort of aligned to the center line. And what we are going to try to do is to see if we can try to understand what is this taxinet doing. Actually, we won't really go inside the taxinet. We'll look at an even smaller module, and we'll try to see what some part of this taxinet, and we'll see what it's trying to do, right? So essentially, the way these systems work is that there are images or video frames. Oh man, okay, I don't know what is happening. So this is supposed to be the taxinet neural network, which somehow showed up very small. And then that gives up, that sort of yields some estimate of the cross-track error. And once again, this is showing up very small. So this eventually goes and sort of controls the way in which the plane is headed. Okay, and so the system that we are talking about here, there's this taxinet controller, which is automatically trying to look at the images and trying to keep the plane aligned to the center of the runway. There is also a safe controller, which could be actually, for example, even a human pilot, or it may be something which is designed to be safe, doesn't optimize performance. And there is a decision module which is trying to switch between these two, depending on whether it thinks that the circumstances are safe enough for the taxinet controller to take the plane on the runway, or it's not safe enough, and the circumstances, the context, maybe the weather, the position on the runway is not safe enough, and so the safe controller should be sort of switched to. So this is of course a machine learning component, but in this particular example, this decision module is another machine learning component. And this kind of looks at a few things like weather, light of day, whatever, the distance from the center and all of that. And it takes a decision that, is this sort of within the operating domain of the taxinet controller, or has it gone outside the operating domain? And if it has gone outside the operating domain, it switches to the safe controller. And what we will see is this decision module, which itself is a machine learning component, small enough, for us to talk about, how does quote unquote explainable interpretations of it look like? Okay, so as I said, the decision module can switch from one to the other depending on the circumstances. And this is, there is already some work that has been done on it. Once again, I have no idea why this aspect ratio is changing here, but this is just saying that there are some previous papers which have also tried to look at the design of this taxinet controller, the design of the decision module. And what we are trying to do is, we are trying to provide an explanation for the decision module, which itself is an ML component. Okay, so once again, so this is our system that we have over here. And the decision module, it takes a decision whether to trust the ML component, which is the taxinet controller. And it takes this decision based on certain inputs like, weather conditions, whether it is cloudy or rainy, whether it's time of the day, whether it is night or day, or whether it is like bang in the afternoon, and also some other inputs like initial positioning, initial heading, and so on. And this is showing kind of the same video where, although it is bright sunlight, but because it started off at the initial position was way off from the center of the runway, so it eventually veers off the runway completely. And here in the next one, you'll see that although it is much darker, and it becomes even darker after that, so all of this is coming from a simulator, since it starts off quite aligned to the center of the runway, the taxinet controller is able to keep it along the runway. So there are these environmental factors, and in this we wanted to examine, can we explain what this decision module is doing based on features like this, the weather condition, time of day, initial configuration, such that even if it's darkish, but if it's starting close to the center line, it can stay aligned. But if it was very bright, but it was starting far off, it veers off. So can we get these decisions? Okay. So the class of interpretations or the explanations that we want to come up with for this work is decision diagrams. But as you will see, once we start talking about the encoding, there's nothing specific about decision diagrams. We could do this for lists and trees and all of that. But these are decision diagrams, and these are kind of the predicates or features. I'm going to use these two words interchangeably here. I mean, of course, if the features are two-valued, they're predicates, but in general, the features can be multiple-valued. So clouds could be, maybe there are 5 different types of cloudy situations. Rain, there could be 3 different types. Initial position could be some measurement bucketed into something, time of day, and so on. And, as Srivash was mentioning, I mean, what is explainability? So once again, by no means this is the notion of explainability. So we'll come up with a score based on how many number of nodes are there in the decision diagram and which predicates we want to use. So for example, the numbers here sort of show our preference for these predicates in the explanation. So we would like the explanation to depend more on the time of the day, and maybe among this cloud and rain, we don't want to make too much of a distinction. It should also depend on the initial position, and I could change these relative weightages in my decision diagram, and that might give me a different interpretation. So the score, I'll actually talk more about the score. This is something that we cooked up for this work, but what I'm trying to say is that there's nothing sacrosanct about the score. You could come up with your own score, and as long as it can be encoded in that max-height formulation, it still works. The framework still works. And the correctness, remember, these two things are what we're trying to balance. This is the prediction accuracy. What fraction of times does the interpretation that we come up with give the same outcome or the same result as the actual decision module? This decision module in our case was, by the way, a decision tree of around 1,000 nodes. Quite difficult to understand what it was really doing. And it was using all kinds of predicates on these features. All kinds of features like this and predicates on the feature values. The other is the explainability score, which is, is it a small decision diagram? Has it used the predicates that I really wanted to make use of? And so on. Right? And, oh man, okay.
So I have a question. So is it the decision module which kind of decides whether to give the control to the taxinet controller or the safe controller?
Yes. Yes. Okay. It is the decision module, and therefore we're trying to understand how it is taking the decisions. What is the logic it's following?
And the objectives of the taxinet controller and the safe controller, they are the same, or is there objectives?
No. They are the same in the sense that both of them are trying to take the airplane taxiing on the runway. But this is trying to sort of also maybe optimize the speed and this and that, fuel and all of that. This is just a safe controller saying, I'll just keep you on the runway.
Okay, thanks.
Okay, so I do not know why these are coming up small. Let me just come out of this.
One question is this, maybe I missed, got distracted. The safe controller is also given? I don't know.
The safe controller?
Is it also given? The taxinet controller is the one for which you're trying to develop, synthesize an explainable model.
So no, I see what you're saying. So the point is, the safe controller, whether it is given or not, yes, it of course matters for the whole system, but for us, we just want to figure out what this decision module is doing, right? So the safe controller is something that we anyway don't get to see the insides of both the controllers. But we are trying to figure, we don't get to see the insides of any of these boxes. We're just trying to figure out what this decision module was doing given that we want to sort of come up with an explanation of its decisions based on these features and predicates on these features. We want to understand how is it switching, when does it switch from one to the other, right? But the safe controller, whether it is given or not given, of course, it has to be given in the real system. For our purposes, we are trying to understand this decision module. So it does not matter what the safe controller is.
So here is a question: the time of the day, how it can be predicate, because it could be morning, afternoon,
Yeah.
night.
So we basically bucket. We say whether the time of the day is between 8 a.m. to 12 noon or 12 noon to 4 p.m. or something like this. So for all of these, the initial positions also we can bucket them. Right?
So, Supratik, why don't you all just, take a lot of data and train a new decision tree with these predicates?
Yeah. So if I train a new decision tree, right, it might be another big decision tree. And
No, here you have specific predicates, right? There are only four layers. Four levels of the tree, right?
No, not necessarily, right? A decision tree is allowed to, it's not a read once kind of thing, right?
No, you have this, okay. So, I thought you have these predicates fixed.
Yeah, we have these predicates fixed, but, for example, in fact, this does happen that, maybe it first checks whether, so whether the cloud is within category 1 or category 2, it wants to take the same decision on the initial position, but after it has split on the initial position, then if the cloud is category 1 or category 2, it can take a different decision. So we don't want to restrict.
It's not a normal tree, is it?
It's a diagram, it's a DAG.
Mm-hmm.
It's a decision diagram, right? You can think of it like a BDD where there are predicates on these features at the individual nodes. But of course, in a BDD, it's read once, but we don't put this restriction. So the framework that I'm talking about, you can incorporate these restrictions, but in our case, we did not. And we actually saw some interesting cases where the same feature is used at multiple positions along a path.
Okay.
One more clarification question, Supratik. So here, I thought that to make the decision, you might also want to model the incremental position as a predicate.
Incremental position.
Yeah, as the plane moves, then it needs to know what the position is to make a decision whether it should let the taxinet controller continue or let the safe.
Okay. Yeah. So what you're saying is that this decision doesn't have to be at the initial starting time. It can take this decision as it is going along, right?
Right. Yeah.
Yeah. So you can think of this initial position as at whatever time it's taking the decision, it's at that point the position of the plane from the center of the runway. Right. So we are talking about the decision that it takes at a particular point of time. This is like a huge, decision tree, as I said. So it's just looking at some values and deciding keep with taxinet or go to safe or go to the safe controller. And we're just trying to understand the decision.
Okay. So it's a snapshot kind of stuff.
It's a snapshot, right?
Okay.
And whatever explanation we come up with, that can indeed be at different possible possible snapshots.
Got it.
So,
thanks.
okay, I couldn't fix this. So there is a diagram of one such decision diagram here, which I think is not very visible, but here I hope this diagram is visible. So this is a very simple decision diagram that actually our tool comes up for this decision module, which is just going based on time. And as you can see, time is like, bucketed here. And this alert is basically saying switch to the safe controller. No alert is saying stay with the taxinet controller. And these are two scores, and I'll tell you how we calculate these scores. This is saying that, well, if you use this model and try to, if you use this interpretation of this decision module, then 60% of the time you can expect to be correct. 40% of the time you may not be. But this is highly understandable. This is highly explainable. So there is a score that we come up with. And this is kind of the score for this thing. And I could also come up with another decision diagram for this, which is slightly more complicated. And of course, what I've gained by that is that my accuracy has increased significantly from 61% to 90%. But of course, this is slightly less understandable, if I can call, compared to the previous one, right? So this is first, deciding based on the position, whether it is between 0.5 to 2.5 or less than 0.5 or greater than 2.5. And then If it was between 0.5 to 2.5, then it splits on the time. Otherwise, it doesn't have to split on the time. Okay, it's basically saying that if the position was quite close to the center of the runway, then the other factors don't really matter much. But if the position was far away, then if it is daytime, then it may still be able to recover. But if it is evening, night or something, then it may not be able to recover.
How does the accuracy of this model compare to the original accuracy?
Original accuracy of what?
I mean, of the whatever.
No, so the decision module is our reference, right? We are trying to come up with a model with an interpretation for the decision module.
So this accuracy is for
how many times are we? What fraction of times does this interpretation correctly predict what the decision module is?
Relative to the original one.
Yeah. I mean, this is our gold standard, right? This is the decision module that I'm trying to find an interpretation. And if this is the interpretation, then it turns out that 90% of the time it gives, right? But if this was the interpretation, only 61% of the time it gives, right? And we will see, I mean, actually there are these three, but the third one doesn't show up. The third one is even more complicated, and it is even less explainability score and even higher correctness score. And we will see that actually none of them are in some sense better than the other, right? But because if you look at these two, this is simpler to understand. This is more complex to understand, but this gives you greater accuracy and this gives you less accuracy. So it is not that I have found a simpler model which has more accuracy, right? So in some sense, they're incomparable. One is easier to understand, but gives less accuracy. The other one is harder to understand, but gives more accuracy. And this is the tension between correctness and metrics that represent explainability. And this is just one possible way of representing, not necessarily the way.
So these accuracy scores are derived in a
these accuracy scores are derived by, we will see how we derive this, right? Yeah. These are with respect to a set of samples, but then this set of samples is chosen in such a way that we can actually give a guarantee on the overall model.
Some probabilistic guarantee. Huh?
Yes, exactly, a probabilistic guarantee. Yes. Yeah. Okay, so therefore, this is our Pareto-Optimal interpolation synthesis problem, that we have a class of interpretations. This is a syntactic class, which could be decision trees, decision rules, which could be saying what predicates you use, which could be actually, all kinds of things. I mean, you could say that I do not want trees which are, or I do not want diagrams which have very large fan outs at the decision nodes. Or maybe it is okay to have very large fan outs towards the root, but not later as we come down towards the leaves. So this is a syntactic class of interpretations. There is a set of samples, and I will talk about how the set of samples is chosen slightly later. But for the time being, let us say we are given a finite set of samples, which is basically a set of input cross output values obtained by sampling the black box, right? And that is why it's okay to treat it as a black box. And of course, the choice of the set of samples is very important. And then there is an explainability measure, which given an interpretation from here gives me a real number, which tells me, how good or how bad it is to explain. It is for purpose of explainability. There's a correctness measure, which takes one of these interpretations, and it takes a set of samples, a subset of I cross O, and it gives me a real number. So it basically says, how correct is this interpretation I've come up with respect to the set of samples? And then I want to find out an interpretation from this, set from the syntactic class of interpretations. Is my cursor visible?
Yeah, it is.
Yeah. So I want to find an interpretation from this syntactic class of interpretations that maximizes this pair. One is the correctness measure for this interpretation that I'm choosing over the set of samples, and the other is the explainability measure for this interpretation that I'm choosing. And of course, as I just showed you, that these two things may be at loggerheads with each other. So we have to define a partial order that, basically it's basically a partial order of a pair of numbers. So if both the numbers, pardon me, was there a question? No. So if both the numbers are smaller, then we say the pair is smaller than, right? If A1 is less than A2 and B1 is less than B2, we say A1, B1 is less than A2, B2. But otherwise, we say these are incomparable. Okay. And we want to maximize, we want to find the maximal elements in this partial order. And that is the Pareto-Optimal synthesis, because the maximal elements are the ones that you can't improve upon further without hurting something else, right? And so the way we are going to solve this problem is we are going to reduce it to weighted maxat. And over the next few slides, I'll just show how we do this encoding as weighted maxat. And there you'll see that it really has a lot of flexibility about how you want to choose the explainability metric and how you want to choose your syntactic class and all of that. So just to recap quickly, what is weighted maxat? You're given a Boolean formula in CNF. So it's a conjunction of clauses. And you're given a weight function which maps each clause to a non-negative real number. And you're required to find an assignment sigma that need not satisfy all the clauses, but it maximizes the sum of weights of the satisfied clauses, right? So for a given assignment sigma, some clauses will be satisfied, some clauses will not be. So you look at only the clauses that are satisfied. So all CIs is that sigma satisfies CI, and you sum up their weights. So here is a simple example. Take this as a CNF formula on 3 variables, and those red things are the weights, the non-negative weights associated to each of these clauses. It turns out that this formula is unsatisfiable. So there is no way, there is no assignment that will make all the clauses true. So I have to throw out some clause to sort of get any kind of, any assignment I choose, some clause will get thrown out. And I want to choose an assignment that kind of throws out clauses with as small weight as I can, so that the weights of the satisfied clauses is maximized. So just as an example, if I take this assignment, I'm not claiming that this is the maximal, this is the assignment that gives the maximal weight, but this is just to illustrate how the weights are computed. So if I take this assignment, x3 is 0, x1 is 0, x2 is 1. So you'll see that the first clause is falsified because both x1 and x3 are 0. So I don't get to add its weight, but all the other clauses turn out to be satisfied. And so I can add up the weights of all the clauses, and this turns out to be the weight is 10, right? So for this assignment, the weight is 10. And my goal is to find an assignment that maximizes the sum of weights of satisfied clauses. Okay, so this is weighted maxat. And what we're going to do is we're going to try to encode the Pareto-Optimal synthesis problem as a weighted maxat problem, and we'll see how that encoding works and then how we use it to explore the Pareto frontier. Okay, so this is our weighted maxat problem. So in order to encode the interpretation synthesis in weighted maxat, we will actually construct 4 formulas. The first formula will be encoding the syntactic class. So every time I find a satisfying assignment of this formula, that satisfying assignment will give me an interpretation in the given syntactic class. So this is not very hard to see what is being done here. I'm probably saying that, that it should be a DAG. So I should have a numbering of the nodes, and then, a node should have maybe, 2 outcomes at least, or 3 outcomes, and then it should have a successor, and then it should, so, this is basically encoding the structure. I'll show you what this encoding is exactly. This is encoding the samples. So remember, we said that we're going to take a carefully chosen set of samples. And these are the examples from which the synthesis is synthesized. So the samples will, lead to the construction of some subformula here. This formula will, this subformula will sort of encode the correctness measure, and this subformula will include the explainability measure. For example, how many nodes are there? What is the depth? Basically, how we want to define explainability. So in our case, we use the number of nodes and the weightage of the predicates used, but we could also encode other things. Right? So we'll have these 4 formulas, and we'll just take a quick look into how these 4 formulas are constructed, so that it becomes clear that we can actually use this framework, for other things beyond decision diagonality.
So Pratik, just a question. It's easy to give two Pareto-optimal solutions, right? I can just give one, which is
exactly. So on the Pareto frontier, none of them dominate the other. So in fact, all of those are optimal.
No, I mean you can give trivial ones, right? I give you just a single node graph, which is very simple, so it scores very high.
Yeah,
and the accuracy is zero.
One extreme. Yeah.
The other one is to just take I'll make a decision tree using your samples. Right? That'll be 100% accurate, and it may be less.
Right. That's true. I mean, particularly the first one that you said that, actually don't even have a decision node. Just always say that it is, whatever, alarm or no alarm. Right. So, so that part, yes, that's one extreme, but probably not very useful. The other part that you said that you can take all the samples and build a decision tree, that decision tree will actually become large. So if my
but it's still optimal, right? Because it's 100% accurate.
Right, but is it admissible within my syntactic class? My syntactic class may say that I only want decision trees with 20 nodes.
Yeah, but then it may also not satisfy your explainability measure, no? Maybe.
Yeah, it will have a very bad explainability score, very low explainability score. No, Deepak is saying that these are two extremes, and indeed these are two extremes. And the one extreme where, I don't even have a decision model. I mean, I just say always output alarm or no alarm. That is always a Pareto-optimal thing. It's probably a useless Pareto-optimal thing, but it's always, because its explainability score is maximum, its accuracy is whatever, probably very low. But the other extreme may or may not be allowed by the syntactic class, depending on if I say that within my syntactic class, I'm only going to have k nodes, right? Because once again, if I make the syntactic class, my decision diagrams very large, I'm probably losing out on how I'm going to understand it, right? So we want to keep these things small. So the other extreme may not fit within the syntactic class, right? But if you remove that restriction, yes, that will also be another easy Pareto point over there. Okay, so we'll see that, we'll construct this formula, and then there'll be certain clauses, we'll assign appropriate weights to them, and then it becomes just this weighted max hat problem, and we'll solve it. So let's quickly, so a solution which gives the maximum sum of the correctness and the explainability score, right? So here I'm having something that is encoding the correctness score, I'm having something that is encoding the explainability score, and the thing that I'm trying to optimize is, remember, it's the sum of the weights of satisfied clauses. So I'll effectively end up maximizing the sum of the correctness score and the explainability score. But if my correctness and explainability scores are non-negative, anything that maximizes the sum is necessarily a Pareto-optimal interpretation, right? Because if both of them are non-negative and if their sum is maximized, it means that I cannot increase one without reducing the other. Because if I could do that, I could have gotten a larger value for the sum, right? So therefore, this is one observation, that if your scores are always non-negative, these two things, I can just plain sum them up and ask for, the weighted max hat for this, and this will give me one Pareto-optimal interpretation, not necessarily the entire surface. So that's how we're going to use this weighted max hat engine to give me one Pareto-optimal interpretation. Okay. So let's quickly look at these formulas, right? So the syntactic class. So as I said,
Supratik, just one question.
Yes.
So there could be more than one solutions also, which
will be. Absolutely, there will be many solutions.
Okay, and so both of them having the same max value, right? I mean, that's possible.
Oh, okay, yeah, that's that's a very good point. So I could have different solutions having the same value for both the correctness, having the same Pareto maximal value for both the correctness and the explainability. That's what you're saying, right?
Yes.
Yeah. So what we did was, in fact, that is true. That does exist. I mean, but the results I'm going to show you today are more about that point. Okay, and what is that point on the Pareto surface? But yes, indeed, each of those points actually can be blown up into multiple interpretations, and indeed this happens. there is no way for us using the two metrics given to us to say that one of them is better than the other. They all appear to be equal using the two metrics given to us. If a third metric is given, maybe we can distinguish them. And therefore, in this talk, I'm going to only pick up for each Pareto point one interpretation. But yes, you're right. For each Pareto point, there are indeed in general multiple interpretations, multiple solutions. But sans any other way to distinguish between them, we are going to pick up only one for this particular talk.
Okay, yeah, thanks.
Okay, so great. How do I encode the syntactic class? So in our case, and you can very easily see that if you want something else, this can be used. So we say that there are maximum of k nodes in the class. There is a set of predicates or features, and a predicate P has a number of branches. I mean, really a feature, how many buckets do we put its values in, has a number of branches or buckets for its values, which is given by BP. And there's a set of labels L, which should be labeling the leaves. Okay. And the way this encoding looks like is, oh, sorry. This is completely bizarre. Okay. Let's see. Maybe I should not go into the. Okay. So can you see my screen now? Is my screen?
Yes, we can see it. Yeah.
Yeah, I do not know why these formulas just didn't show up. So this first formula says I'm using a Boolean variable lambda IP, which is there are k nodes in the decision diagram if node I is labeled by the predicate or feature P, right? So there's a finite set of predicates, finite set of nodes. So I'm sort of using this variable to denote if the node I is labeled by the predicate P. And all this is saying is that for each node, it can be labeled by only one predicate. Once it's labeled by one, it cannot be labeled by the others, right? The second one is saying something interesting. It is saying that if a node I is labeled by predicate P, and this is for each node and for each predicate, if the node I is labeled by the predicate P, then that node should have number of outgoing branches or children, which is exactly the number of branches for that predicate or feature, right? So if the node I is labeled by P, then for number of children, which is between 0 and BP, I should have these Boolean variables true. And what is this Boolean variable saying? It's saying if the cth child of node I is node J, then this tau ICJ is true. Otherwise, if the cth child of node I is not node J, then tau ICJ is false. So here I'm saying if the node I is labeled by predicate P, then how many ever children that predicate P, how many ever branches that predicate P gives rise to, for each of those, I should have a node which is going out from I to that node, right? So I should have for all C in 0 to BP, there should be some node, and these nodes should have an index greater than I, because I want this to be a decision diagram. I want this to be a DAG. So they're all topologically sorted. And there should be an edge going out from I to this jth node, and this should be one of these C children or C branches. And of course, if a edge goes out from the ith to the jth node, then for all other j, I mean, there can be only one edge going out from the ith node to the jth node. I cannot have other edges going out from the ith node to other j nodes. So this is just encoding the structure that if I label a node by a predicate P, then it must have so many branches, and each of those branches must go to another node, which is labeled by a higher index, basically ensuring topological ordering. And the third part says that, maybe a particular node is labeled by a predicate which has only 2 branches, but there is another predicate which has 10 branches, right? So I should ensure that if a node I is labeled by a predicate P with just 2 branches, then there should not be an edge out of this node for any C greater than 2, right? So for all C that is greater than BP and up to the maximum, there should not be an edge out of this node. So it should not be the case that I've labeled a node with a predicate P which just has 2 branches. And then in the decision diagram that I'm constructing, I also have a branch which is the 7th branch going out of this node. That should not happen. So for all C which is greater than BP, this should be false, which means there should be no, and for all J which is indexed higher, there should be no branch going on from I to J, which corresponds to the CF branch. This is just encoding the structure. And what I want to sort of highlight is that this is for the decision diagrams, we wanted to do. If you want to encode a tree, if you want to encode a list, if you want to encode a decision diagram, which is fat at the top, narrow at the bottom, these are just constraints over here. Okay. The next thing is about the samples. And for the samples, okay, if I can't show the animations, it will be bad, but I hope it, okay, this is good. So for the samples, for each sample and for each node, I will have a variable, which I call MIS. And remember, a sample is just an input-output pair. And this variable MIS will be true if and only if the interpretation that satisfies phi E, remember this phi S, I'm going to conjunct with phi E, and every satisfying assignment of phi E gives me a decision diagram, some interpretation. So if the interpretation satisfying phi E has a path from node I to a leaf labeled O. Remember, this sample is telling me if you give me this input, this should be the output. So these outputs should be labeling the leaves of the decision diagram, and these inputs are basically being used in the predicates in the decision diagram. So for each sample and for each node in the decision diagram, which corresponds to a satisfying assignment of phi E, I will say that for each node, for each sample, this variable is true. If in that interpretation corresponding to phi E, there is a path from the node I to the leaf that corresponds to this output. Okay? Essentially saying that this interpretation can map I to O, because in this interpretation, there is a, I mean, if in this interpretation, okay, I think I have unfortunately overused I for two things here. This is the input. This is a node I. So whenever I say I as a tuple for the sample, it's really the input. Yeah, I'm sorry about this. This should have been maybe INP, and this should have been INP. So this variable is true for a particular node in the interpretation if starting from that node, given the sample, I can actually reach the correct leaf. Right? There is a path starting from node I to the leaf labeled O, and this path can be followed using the values of the inputs, right? Which are the things that are going to be checked in the different predicates. So how do we encode this? This starts at the leaves. So we say that if I have a leaf whose label is already matching the sample's output, then of course for this starting from that leaf, there is indeed a path to that leaf, which is labeled by that output of the sample. So this is easy. But for other internal nodes, we actually use this encoding. And so, maybe in the interest of time, I will not go into this full encoding, but it's really saying that, if I mean, at node I will say that there is a path which leads me to the right leaf. If I know that, at node I, given the predicate P, which branch am I going to take? And for that branch, the child corresponding to that branch was actually taking me to the right leaf. Right? So it is really saying, look at the predicate that is labeling node I, see for this sample, which has the input values, which branch of this predicate gets taken. And then if that branch contains the node J, then from node J, there should be a path to the right leaf. Right? MJS is basically saying there's a path to the right leaf. So MIS is equated to this. And this, I think, is fairly standard. This is just saying how do you measure accuracy. For each sample, if I come up back to the root and I ask whether M0S, if the root is index 0 or 1, let us say, if I ask, is M1S true? It means for that sample, okay, is there somebody trying to say something or? I just heard a beep. I don't know. Hello?
Yeah, we can hear you, Supratik.
You can hear me? Okay. Thanks. So this MIS is a variable which just says that for sample S, starting from node I in the interpretation, I can actually go to the right output. So if I look at M0S, it's saying for sample S, starting from the root, I can go to the right output. And we would really like to have as many of these M0S true as possible, which means we'd like for as many samples as possible from the root, I should be able to go down to the right leaf, right? And this is kind of inductively defined on the structure of the decision diagram, saying that, well, if your child had the right, if there was a path from your child to the right leaf, then there's also a path from you to the right leaf. Okay. Then there's this correctness measure. And
yes. So Pratik, I have a question.
Yeah.
So all these formula, at least so far, they have parameterized these indices with respect to the size of your diagram.
Absolutely, absolutely. Yeah.
So when and where do you fix that? Yeah.
Oh, that is in the syntactic class itself.
Ah, I see. So there you are. Oh, size K. Okay,
Yeah.
I missed that.
Yeah. So actually, it turns out that this number grows very fast, right? I mean, you have K nodes, and then each of the nodes could be labeled by a predicate P. So there are already, right? I mean, P raised to K ways of labeling the nodes. And then there are branches, and then each of those branches could go to any of the other nodes as long as you have a topological order. So this number, even for small values like, let's say if I say K is 20 and there are 10 predicates and 10 labels, this number really becomes very big. Which is the space of decision diagrams or whatever interpretations in the syntactic class. But the formulas that we are constructing are all polynomial in these numbers. Size K and the number of predicates, the number of labels, right? Because, I mean, I just showed you how I'm constructing the formulas. There is no exponential blow up here. It's kind of...
I have a question. Like, should there be just one path to the correct node, or it can go to the correct node, or it should go to the correct node, the path?
No. So if you look at a predicate at a decision node, it is basically some feature, right? And that feature is going to have a certain value. Let's say it's some part of some subset of the inputs in that sample, and that subset of the inputs are going to have certain value. And now we are bucketing the outcome of that, whatever the value of that feature is, into, I mean, I guess I had showed somewhere earlier when I was showing the decision diagram. So these things are disjoint in our case. So then there is only one path that it can take. But if these things are not disjoint, there are multiple paths that can be.
Okay. And
is that your question?
Should there be one path at all? Like, can the decision diagram have a wrong leaf, a path to a wrong leaf node as well? Is that also admitted?
Yeah. I mean, so what I'm saying is that given any decision diagram and given any input, it will take you to a leaf, right?
Okay.
Whether that leaf is the correct leaf or not is what is being encoded by this M variable, right? So it is saying that if starting from node I, which could be the root or which could be some intermediate node, if I start evaluating the predicates on whatever that sample is, if I reach the right node, if I reach the right leaf, which matches O, then MIS will be true. Otherwise, MIS will be false.
Okay.
Right? And our goal is to make as many of these MIS true as possible. Right? In particular, I should be bothered about the root, because that's where the decision, that's where I start coming down the decision diagram. And so if for each sample I can make M0S true for each sample S, then I know that this decision diagram will match the samples, will match all of the samples, will match the outcomes in all of the samples, right? So then it is kind of, for this sample set, it's perfectly modeling the black box ML.
Okay.
Right? Okay. And
one
for the
question.
correctness.
Sorry.
Yeah. Yeah, go ahead.
So one question that I have is, does this mean that if suppose we have some decision diagram for which M0s is never true, but let's say M5s onwards is true, like it is, so this MI is for each node in the decision diagram. So if it is true from some node onward, but not true for the actual
It can happen,
starting
right?
node, yeah, and then we would assign a good score to such a decision diagram, right?
No, because we will see. So it depends on what am I trying to optimize, right? So this correctness measure, it is
Right.
just on the M1s.
Okay, sure.
So this is what I finally care about. So I would want all the M1s to be true ideally, right? But remember, I showed you a CNF formula where not all clauses can be made true, only some of them can be made true. So maybe not all of these can be made true, only some of them can be made true, but these are the ones which I'll try to maximize.
Okay.
Right? So I will associate some weight to each one of them and I'll try to maximize.
Okay.
Right. And the explainability measure, so in our case, we use the number of nodes and the predicates, right? Each predicate had some priority. But once again, this could be anything that can be encoded up like this. So for example, in our case, we said that the root, so this UI denotes where the node I is actually used. So the root is always used. And we say any node I is used if I look at, what are the edges going out of that node. If I look at what are the edges coming into that node, and one of the edges coming into that node is used, right? So a node is used if there is an incoming edge from a used node. And this incoming edge, of course, has to be, an edge coming from another node corresponding to a certain bucket for its feature values, right? So we define this node used predicate like this for all nodes. And of course, we say that the root has to be used. So it's basically saying the root has to be used, and therefore wherever the branches go out from the root, they are marked as used. Wherever branches go out from them, they are marked as used. But anything which doesn't have a used thing as a predecessor, that gets marked as not used. And then I want to make sure, because I would like to use as few nodes as possible. So I would like to have UI bar or negation UI for all the nodes, right? And then I would like to maximize the number of these unit clauses that are satisfied. And of course, I may not be able to satisfy all of them, but if I can maximize the number of nodes that are not used, then I have minimized the number of nodes that are used, right? And then there is this predicate business also that we choose, which is we say that if a node is used and it is labeled by a predicate P, then we have this variable which we set to true, which is really used for the counting. These predicates here will have the weight of the predicate P. I showed you initially that different predicates can have different weights. So I would like to maximize this, but this clause here, this is a unit clause here, this will have the weight of the predicate P. So it effectively means that I'm trying to maximize the weights of the predicates that I'm using. So the node has to be used and it is using predicate P, and I'm sort of giving the weight of the predicate P to this variable over here. But, this is just a simple illustration. You can say that, for example, you can say my correctness measure is the square of the distance from, what this decision diagram is predicting as the final output and what the actual output is. And this is fine because the square of the distance can actually be encoded up as in a polynomial size circuit, and we can just put the formula for that, right? Similarly, we could say that here, I don't want the depth to be too large, so that I can sort of say that I should not have, basically, it should not be the case that I have a node which is used and then its parent is used and its parent is used and its parent is used for 5 times, right? So these are the kinds of things that we can encode on the structure over here. But by no means this is the only way to encode explainability. This is just an illustration. Okay, so once this is done, what I'm going to do is I'm going to say assign, and over here, remember I said I would like to maximize how many ever matches I get. But even here, I could say that some samples are more important for me, some samples are less important for me. So depending on some of these samples, smallest, I could assign a higher weight. For some other samples,
Supratik, there is some question on the chat.
Oh, I'm unable to see the chat. Can somebody please read
Maybe
it?
I'll repeat it. This
Yeah,
from
can you please?
Shaunak.
Yeah.
Sir, as you mentioned, we could ignore some of the clause to get the maximum SAT.
Yes.
Also, you said about if there is a path from I on S, we can always have a path. If in the worst case, we ignore all the clauses.
Oh, but if you ignore all the clauses, then you will not be able to maximize the score, right? I mean, remember, our goal is to maximize the number of these things, right? So if you say I'm going to ignore all of them, basically I'm going to let all of them be 0, then I'm not going to be able to maximize this. I mean, yes, it will be some solution, it will have some weight, but it will not have the maximum weight.
But he says that but there will be a path. Yes.
No, if there is a path, then this is true, right? Because that's how we defined it, right? If there is a path, so MIS, if and only if. So MIS will be true as long as it is labeled by a certain predicate. And for that predicate, when I feed the inputs from sample S, I go to the cth child. Right? It's like the sample S may say time of day is 9 a.m. and the predicate or feature might say, okay, what is the time of the day? So 9 a.m. will go to the 8 a.m. to 12 noon bucket. So that will maybe the first bucket. And then the child of the ith node, the first child of the ith node must have, so whatever J satisfies this, which is the first child of the ith node, MJS has to be true. Only then MIS can be set to true. So if there is a path, then MIS will get set to true. And if MIS is not set to true, then this path doesn't exist because there's an if and only if. Right? Okay. So, Madhukar, you have to tell me how much time I have left. I know I have exceeded the 1 hour thing. Madhukar or Deepak, maybe. Can I take 5 more minutes? Or?
Yeah, Supratik, I think can wrap up another 5 minutes.
Yeah, okay, great. Okay, so what we are therefore trying to do is we are trying to assign a weight to each of these unit clauses, and these weights could depend on the samples. We're assigning weight to each of these unit clauses could depend on the predicates, and we are maybe saying assign a weight of 1 to each of these so that the number of nodes is minimized. That's based on the metrics that we chose. And then we feed it to MaxSat, and MaxSat gives us a solution which maximizes this sum, right? And as we just discussed, if the sum is maximized, since all of the weights are non-negative, that solution from MaxSat already corresponds to a Pareto-Optimal solution, because I cannot improve one of the scores without hurting the other, because if I could do that, I could find a higher value for the max value of the sum, right? So, so basically, yeah, what we try to do is we get this 1 point, right? We feed it to MaxSat solver, and the MaxSat solver gives us a solution, and we say, okay, yes, that is certainly one Pareto-Optimal point. But the moment we got a Pareto-Optimal point, this is the space of explainability score normalized to 1, the space of accuracy score or correctness score normalized to 1. And once we have obtained a Pareto-Optimal point, we immediately see that there are 4 regions that this space gets partitioned into. There cannot be any solution here, because otherwise this wouldn't have been Pareto-Optimal. Here, the solutions are not Pareto-Optimal. This point dominates it. And so there are really these 2 regions that we have to work. This is the region where we can get higher correctness score, but possibly lower explainability. This is the region where we can get higher explainability, but lower correctness. And so what we do is we continue the search in region 3 and region 4. And how do we continue the search? The naive way to do this would be to say, okay, add a constraint saying that the explainability score should be between such, and the correctness score should be between 1 and 0.6. And similarly over here, turns out that, I mean, that is the naive way of doing it, but that doesn't really scale very well. And the reason if I could do that, of course, I could get another Pareto point here and another Pareto point here, and I could keep repeating this process. But the challenge is that the number of samples is too high, and therefore, if I'm going to change these bounds on the correctness score, remember the correctness score, the formula depends on the number of samples. And if I have to say that, well, the sum of all the MIs has to be less than something and greater than something, then I'm basically, every time I'm introducing a huge formula, because there are these M1S exists for each sample S, and there may be thousands of samples. So every time I introduce a constraint on the correctness score saying the sum of M1S has to be between some lower bound and upper bound, it actually blows up the size of the formula quite a bit, and that doesn't scale very well. So what we did is we said, okay, we are not going to keep the correctness measure. We are just going to set upper and lower bounds on the explainability measure. So this sounds strange, saying that, I wanted to search this region R3, but I'm going to search this entire region, which is less than this 0.7 explainability score, including this region R2. But the way we handle it is that we say, okay, let's get a Pareto point there. And if this Pareto point is already in this rectangle, we keep it. But if I get Pareto points which are here, then I just discard them. And it turns out that this way, where we are not blowing up the size of the formula by putting limits on the correctness score, which depends on the number of samples, which is quite high, but we are actually saying, let's just put limits on the explainability score, which is independent of the sample. It just depends on the structure. And then if I get something which is already Pareto dominated, I just throw them out. So we get some redundant calls over here to max that, but this turns out to be much, much more efficient. Okay. And now, what are the statistical guarantees that we can get? Remember, we did this whole thing with respect to a set of samples. Now, why should that work in general? I mean, it may work, it may be Pareto-Optimal only with respect to those samples. Why should it work in general? And so, how do we choose the set of samples? So here, and of course, obtaining an exhaustive set is out of the question. So how large must our set of samples be so that, we are not overfitting the set of samples? And this we appeal to PAC learning, probably approximately correct learning. And I sort of have the definition of that here, but let me not get into the details of the definition. But basically, PAC learnability actually tells us what is the minimum number of samples that you must have, such that when you find the optimal interpretation with respect to that many number of randomly chosen samples, independent and identically distributed randomly chosen samples, then you can also say that when you run this interpretation on the overall model, then you're not going to incur too much error from the best thing, right? So PAC learning is basically saying that you have a class of interpretations, and then you want to choose the best interpretation from within that class over all samples. But then you can't look at all possible samples. So what you do is you look at a small subset of samples, and with respect to that subset of samples, you find the best interpretation. But if this subset of samples is chosen, sufficiently large enough, which depends on these two parameters, delta and epsilon between 0 and 1, then you can guarantee that whatever interpretation you choose with these sufficiently large set of samples, that same interpretation is not going to deviate too much from what the best interpretation in this class would have done with very high probability, right? If the best interpretation in this class would have had some, loss function or whatever, in our case could be accuracy, then the probability that what I have synthesized using a large enough set of samples, but not the entire set of samples, the probability that that is going to make an error which is very different, which is very far away from the error made by the optimal interpretation in this class, will be low with high probability. Okay, so this is standard PAC learning. It turns out that every finite class of interpretations is PAC learnable. This is a basic result in PAC learning theory. And of course, this immediately means that if the class of interpretations we have is finite, then it's PAC learnable. I mean, we can apply this technique. It doesn't have to be finite. It has to have what is called finite VC dimension. But in this talk, we are just calling it finite, large but finite. And then the loss function that we use is also something, that needs to have some property. And in our case, we can make it have that property. And so the number of samples can be determined in terms of the value of epsilon, the value of delta, and the size of this class of interpretations, right? Very thankfully, it is logarithmic in the size of this class of interpretations. So therefore, even if this class is very large, the number of samples is still manageable. And so we basically do that. As a result, just to conclude, maybe in one more minute, this was our the thing what we set out to do, and this is kind of the results that we get. So this is the delta E, delta C space. These blue points are Pareto-optimal points here. As RD was pointing out, each of these points, actually, if you zoom into them, there are many interpretations corresponding to each of those points. However, they are all equivalent with respect to these two metrics. If you give a third metric, maybe it is possible to distinguish them. But this is how it looks like. And this is kind of the key takeaway from this, is that it doesn't make sense to give one interpretation. All of these are Pareto-optimal, right? So it doesn't make sense to give one interpretation maybe like this and say that, yeah, this is the best possible way to explain this. It's not the case. I mean, this may be the best possible way to explain this if you wanted a good correctness and a good explainability score, but not necessarily the highest explainability score or the highest correctness score. If being correct is very important for you, then probably you should be here. If being highly simple explanations is very important for you, you should be here. But at least from these curves, we can see that there is a knee around this point. And so these points are probably good trade-offs. You can get both high accuracy or decent accuracy and decent explainability. But this is the picture that was completely missing in the earlier literature, which were trying to obtain an explanation for a given black box model. It's really a surface there. There is no one single explanation. And here I've just shown you that this point corresponds to this. You can see that it is not maybe so easily understandable, but it has a very high correctness score, 94%. This point corresponds to this. It is much more understandable than this, has a higher explainability score, but is less accurate than this. And this point corresponds to this, which is the simplest, but it has a very low accuracy score. And so, I mean, depending on what you want to use this explanation for, you have to choose between one of these. So this choice should really be with the user. And we have done this experiment with other things also, like, some bank loan examples, some theorem prover example. And in all of those, we get these curves. Okay. Oh my God. Okay. So there is a table here, which once again doesn't show up very properly. Maybe I should just come out. Yeah. So here it shows up much better. So these are the delta and epsilon values we used. These are the sample sizes. And this is saying how many Pareto-optimal points were there. And this is the total number of points we had to explore. Remember, some of those points we had to throw out because they were already Pareto dominated. So we are making multiple maxat calls, right? Here, 25 maxat calls were made. What is the minimum time? What is the maximum time? Median? And when we found unsat, how much time did it take? So this is kind of the picture. And so in summary, what I presented was synthesizing interpretations of black box models. There is really no one unique interpretation. I mean, there are conflicting objectives, and so the best we can hope for is Pareto-optimality. We tried to solve this using maxat. There are limitations of this. I mean, we are basically limited by how much maxat solvers can scale. So we are currently looking at ways to bypass that. And we can give these pack guarantees based on, by choosing the number of samples, right? And then, in ongoing work, we are trying to extend the interpretation classes to infinite cardinality, but finite BC dimension, oracle guided approaches for defining interpretations, alternatives to maxat, like incremental maxat or anytime maxat for the exploration process. So with that, I'll end. I'm sorry I overshot quite a bit. If there are any further questions, I'm happy to take them.
Okay, thank you, Supratik. Any questions?
Hi. Hello.
Yeah, hi, Digant.
Yeah, I have one question, which is, if somebody were to suppose want to use a framework like this for debugging an ML model, say they have a situation where the taxinet, this decision module is handing over to the or it's doing something wrong. It's going it's doing something that is wrong very clearly from the human designer perspective.
Yeah.
Could there be a way to add something here or ask for an explanation of that situation specifically within this framework?
Basically, you restrict your samples
Okay.
around that environment, to around that context, and you get it. So this is the kind of new part I think that we have in this, is that the user chooses what set of samples, what is important for the explanation, what kind of explanation. And so for the case that you mentioned, I could say that, maybe I'm seeing actually what we ourselves did was, I mean, we looked at this and we said that, okay, it looks like under certain conditions there are going to be a lot of alerts, right? I mean, if it is cloudy and the time is between whatever in the night, there will be a lot of alerts. Or if the position is, even in the day, the position is greater than something, there'll be a lot of alerts. And so we said, okay, can we just focus on these kinds of environments, right? Which basically means that I'm now restricting my sample space not to be IID over the whole, whole space, but I'm restricting it. I'm saying I want clouds here and I want the time here, and give me samples from these, right? And then when I look at the explanations for those, that explanation would basically, it can actually give a more refined view of what's happening in this part. And yes, so in fact, one of the usages of this is for debugging. The other usage that we've been trying to use it is to see whether, if I look at a model whose accuracy is high, and then if I obviously see that it is biased towards something, then it's probably the network is biased, right?
Right.
Because this is having a high accuracy, and I can see from here that, most of the times for most of the cloud things, I mean, for example, here it does look like for most of the cloudy things, it is going to give us an alert, right?
Yeah, so it's probably biased towards
it is
that.
probably biased, and then we could actually go and examine this. We could say that, okay, this is the feature on which this appears to be biased, and so let us create samples which keeps everything else the same and just varies this feature. And we could come up with explanations for that, and then the bias sort of gets amplified in the interpretations that we see. Right.
I see. So I just have one follow-up about this. So you're saying that, so basically we're doing this debugging to look at sort of some smaller subspace of the behavior in some sense. We can do some sampling. Instead of taking IID over the whole range, we'll take some other distribution of
Not
it.
just some sampling. We actually know what subspace to sample, right?
Right.
It is clouds between 0, 2, 3, and 4, and the time either between 12 p.m. and 8 a.m. Or if the time is between 8 a.m. to 12 p.m., then it should be greater than equal to 2.5. So we actually have all the conditions, right? And now we say that, okay, give me samples satisfying these conditions.
Okay.
Right? It's not just arbitrarily saying,
so
give me some subset of samples.
Yeah, so basically the question that I have with respect to that is the only sort of link between this explanation model that I have and the actual decision model is these samples. So in that case, if we are actually tunneling down and looking at a smaller range of values in the samples, maybe somehow the original decision model learned something wrong because of things it saw in a completely different part. Would that still be captured, or
I mean, the decision module was trained using a biased training set. Is that what you're saying?
Yeah, so basically, if the decision module is doing something that is, so in some sense, if the decision module is going wrong in one particular one limited set of behavior,
for some features, for some feature values.
Some very small range of features.
Yeah.
So let's say only for cloudy situations, then the diagram that I get, the explanation that I get from there versus the explanation that I might get for all possible number of samples, they like, is there some way we can say something formally about how those two things might be related? Because when we're like removing some of the samples, we can't like, can we say something about how these two things are related? Can we say that this is in fact the same, an explanation for the same model? in some sense, or is it just that we're seeing a different set of data
No,
and we're
it is not the same model. And basically what we can say is this, that there is a certain distribution over this space of all samples. And if I skew this distribution, and if I want to find out, what is the explanation, what is the best explanation over the skewed distribution, then we have to choose our IID samples according to that skewed distribution.
Right.
And the model that we get from that skewed distribution, we can again give this pack guarantee over it.
Right.
But the model that we had over the whole space, we will get a pack guarantee over that whole space.
Right. So those two models will have sort of two different kinds of guarantees behind them.
Exactly.
Okay. Yeah.
Okay.
Yeah. Okay.
There are no further questions.
How do you choose your predicates?
These are, in our work, this is a very good question. In our work, we say that it is user provided, but actually the more practical way of doing this is saying that take the black box model, take the set of samples, and ask a decision tree generator, any off-the-shelf decision tree generator, to generate a decision tree, which might generate a very big decision tree, which may not be understandable at all. But then it has chosen some predicates that it found to be useful. And then we could pick up that set of predicates and say that now I want you to do all of this, right? So the choice of the set of predicates is something that we are outsourcing to some other thing. It could be just a decision tree learner.
So there is such a thing called decision tree generator, is it?
Oh, there are decision tree learners. Yeah, absolutely.
Okay.
Yeah, I mean, the only thing that you get there is that unless you make these decision trees very small, you say that not more than so many nodes, not so much height and things like that, they are often not very understandable. I mean, if you want to see an explanation for this, I mean, you can see here, I mean, this is kind of like, nothing deep here, that a decision diagram can be exponentially more succinct than decision tree, right? Where did it go? I mean, it's sharing subgraphs. Yeah, so this one, if I were to expand it out into a decision tree, I will have many more nodes, and that would, I mean, even if it is using the same predicates, it would look less understandable. But I can pick up the set of predicates, and then I can say, here is my prioritization, and give me. But the answer to your question is that this is user provided, possibly from other tools that generate explanations.
So
just Pareto-Optimal. Yeah, go ahead.
So a couple of things. One is, has the learning community studied this problem of given a set of samples but given some bounds on the resources for the nodes? And
yes, absolutely. So as I said, in fact, there's a lot of work on this. So
do they have a notion? I mean, do they come up with something optimal anyway?
Yes. So they combine these two metrics into, so typically that is the large body of work, where they combine these two using some weightage.
Okay, they don't separately optimize.
Yeah, give me something which will that becomes the objective function to optimize when they're building these decision trees or whatever. There is also some work which tries to look at these as multi-objective optimization in the learning community. It is it doesn't use MaxSat. It uses optimization, and then of course, oftentimes you settle for something which is a local optimum, not necessarily a global optimum. So we can't give guarantees about Pareto optimality over there. You can just say, okay, this is something which is looking good, right? But of course, the same criticism can be applied to what I just talked about, that what if the weighted MaxSat solver cannot give me the maximum value if I have to rely on some anytime MaxSat solver? Yeah, so it is the same problem over there, right?
So does your encoding give you a guarantee that if you get a MaxSat solution, that what you get is optimal?
Yeah, yeah, yeah.
That
Because
guarantee is there.
yes. So right. So I mean, remember what we are maximizing is, I mean, let us say each sample is equal. So the sum of, so each of these clauses here, the M1s, they have a weight of 1. Each of these lambda prime IP has a weight, which is the weight of the predicate P. And each of these UI bars has a weight of 1. And all the other clauses have 0 weight, right? So whatever it is maximizing is really the sum of these things. So it is trying to maximize the sum of how many samples am I going to give the right answer? What is, and the sum of these two, I can think of it as the explainability score. How few nodes are used, how many nodes are unused, and what is the predicates that are used. What is, and when it maximizes the sum of these two, that is necessarily a Pareto point, because if it was not a Pareto point, I could have obtained a value of the sum greater than this, what I have gotten right now, right? So therefore, we actually use it to get one Pareto point. And after that, we divide the space and re-invoke it with the other Pareto points. Yeah.
Okay. Okay, any other questions?
Yeah, I have one question.
Yeah, go ahead.
So, as you said, we are choosing some particular samples based on some properties. Isn't that making the samples dependent?
They're not based on any property. So the only property is that, okay, so if I can go over this. So we are saying that there is a class of interpretations, let us say a class of decision diagrams. There is, this entire set of samples, right? All the input output behaviors that you can provide to this. So this class of interpretations is said to be pack learnable with respect to this set of samples. And of course, a loss function, right? I mean, how do I say that one interpretation is worse than another one? So there has to be a loss function. So we say that, this class of interpretations is pack learnable with respect to this input output space and a loss function L, if it is possible for us to find this thing called the sample complexity, where I'll give you a delta and an epsilon between 0 and 1, and this will return a natural number, which has the following property, that for every delta epsilon you give, and for every distribution over this entire space of inputs comma outputs, if I ran this algorithm over, what is this algorithm? This algorithm is trying to return the best interpretation for a subset of these samples. Right? When I run this algorithm on at least these many samples, which have to be sampled according to the distribution D. So if you want to find out, a good interpretation for samples which are distributed according to some distribution, you have to generate your samples, the smaller set of samples, also according to the distribution, right? And the algorithm returns an interpretation E such that, right? I mean, this E is what you're getting by saying this is the best interpretation in this class for this small set of samples. So in our case, this is a Pareto-Optimal interpretation for the given set of samples, right? But then actually, yeah, I mean, this is the interpretation which maximizes that sum of the weights that I showed you for the given set of samples. And the guarantee that we get is that the interpretation that it returns, I mean, basically whatever we are getting from that solving that MaxSat, the Pareto-Optimal interpretation, it has this property that if you took that interpretation and ran it, so this is the loss function of the given interpretation over the entire sample space distributed according to distribution D, right? So if you use that interpretation over the entire sample space distributed according to the distribution D, you will get some loss function value. And if you took the best loss function that you could have obtained from this class of interpretations when considering the entire sample space, then the difference between these two cannot be very large with very high probability. So the probability that the difference between the loss function of what you got evaluated over the entire sample space distributed according to D and the best interpretation that you could have gotten, its loss function evaluated over the entire sample space, the probability that this difference is less than or equal to epsilon is very high. So think of, I mean, for example, we took delta as 0.05 and epsilon is 0.05. So we are saying that with 95% probability, we know that whatever loss function our chosen interpretation is getting, by just looking at this smaller set of IID samples sampled according to the distribution D, whatever loss function our chosen interpretation is getting is going to be within 0.05 of what the best interpretation in this class could have given you over the same entire input space according to distribution D. So it is actually dependent on the set of samples, of course, because we are using the set of samples to interpret it, to synthesize the interpretations. But this probabilistic guarantee basically means that if I repeat this process, let us say 100 times, so I get a sample of size 300, I get a Pareto-Optimal interpretation. I get another sample size of 300 independently chosen, I get a Pareto-Optimal interpretation. If I repeat this, let's say 100 times, then 95 out of those 100 times, whatever I would have gotten would be close to what the optimal thing in this class of interpretations is, right? So if I just do it once, of course, that could be the worst possible thing, because you could get an interpretation which is very, very off from the ideal one, from the best one, with non-zero probability, right? So this process that we're talking about has to be repeated. So you get a set of samples, find the Pareto-Optimal interpretations, get the next set of samples, find the Pareto-Optimal interpretation, get the third set of samples, find the Pareto-Optimal interpretation. And so maybe you get 10 or 100 such Pareto-Optimal interpretations. And the guarantee that you have is that 95% of them are close to the optimal. Which of them is close to the optimal, that we don't know, that we can't find. But now if I have all of these, I can take a majority voting amongst them, or I can use some ensemble vote, ensemble decision techniques, and then I can improve the chance that. Does that answer the question?
Yeah, yes, I got it. Thanks.
Yeah, help us go approach
Okay, Supratik, yeah, so thanks a lot.
Yeah, okay, yeah.
Very
Thanks
interesting
for
talk, and thanks to everyone for the interaction.
Yeah, okay, thank you.
Thanks for joining. Yeah.
Yeah, if there are any further questions, please, anybody feel free to email.